it's time for Emanuele Greco.
Yes, can you hear me?
Okay, we can give some time to the Minds people, to stop the recording and start the new one, or I don't know if everything will be in a row, but anyway, I say this. So Emanuele can share the screen.
Yeah.
Nice to meet you too, and I also look forward to your talk, because this is very related to what we've been discussing with supernova physics and the mechanism of explosion of supernova and core collapse. We see your pointer, we see your slide. Yeah, that's perfect. So, okay, thanks a lot for being here, Emanuele, and the stage is yours about possible indication of a neutron star, right, where the supernova 1987A was. Please.
Yeah, thank you. Yes, in this talk I will discuss some recent results about which suggest the presence of the neutron star in supernova 1987A. Before going into details of the analysis, I will just go briefly try to recall the supernova remnants characteristic, which maybe are not very familiar with some audience. Basically, the X-ray plasma supernova remnants is ruled by the expansion of two shocks. The primary shock, which expands outwards facing the interstellar medium, and by shocking it brings it to a temperature of the order of 10 to the 7 Kelvin, and also with the reverse shock, which moves inward in the remnant facing the ejecta, which are basically the stellar fragments of the progenitor star now expanding into the medium. The key parameters which rules the emission of the X-ray emission of these sources are the temperature, as I mentioned, the emission measure, which is basically the integral of the volume of the emitting region of the square density of the electron square density. The ionization parameter, which tells us in the ionization state of the plasma that is in the supernova remnants, and this is because of the interaction between the plasma itself, the gas itself, and the shock. Basically, we have a plasma which is out of equilibrium if this value tau is lower than 10 to the 12 seconds per centimeters cubic. A very important element is also the abundance, because it tells us which is originating the emission that we're actually detecting. So for abundances which are lower or compatible with 1, we know that we are looking at a shock interstellar medium emitting, while if the abundance that we measure is higher than 1, that means that we are looking at ejecta. And last but not least, we also have the absorption, which shapes the morphology of the spectrum, especially in the lower energy band of the X-rays. So since I will tell you a bit about thermal emission usually during this talk, I want just to give you an idea of how the thermal X-ray emission looks like in supernova remnants. We have line emission, which is basically just a transition between bound states for the ions. The radial recombination continua, which is due to the recombining of electrons into the ions, and finally also the Bremsstrahlung, which is basically just the free transition of the electrons interacting with through Coulomb interactions with the ions. Finally, there is also a true gamma emission, which usually is not very important for these targets. So supernova 1987A, Manibrata already told quite a bit about it, and basically it is the most recent naked eye visible supernova. It's exploded in a Large Magellanic Cloud, and it's particularly important because it represents a unique laboratory to study the link between the progenitor stars that we know because we were observing it, the supernova which exploded, and the remnant which is now developing in the Large Magellanic Cloud itself. It is embedded in a H2 region, and it is interacting with a very dense ring-like structure, which is very visible here in this multi-wavelength image, where you can see, for example, in green the optical data, and in blue one the X-ray ones. And it is characterized by one thing, which is the only remnant that we are aware of, that its reverse shock has not hit the inner ejecta yet, because of the very young age of 87A, which is only 35 years old. Because of the not emission, because the ejecta are not being heated yet, we do not clearly see any radiation stemming from the internal part of 87A. And then we also have the cold ejecta, which might actually hiding any kind of radiation stemming from this area. Indeed, what we are missing from this very studied object is a clear detection of the compact object of the neutron star, which we expect should be present in this source, because we detected neutrinos emitted during the explosion of the supernova. But again, this compact object has never been observed. The only hint that we had until 2 years ago was this detection by Signal collaborators in ALMA data, which showed that a blob structure, which is here highlighted by the cyan ellipse, whose emission is somehow compatible with what we might expect from a protopulsar with nebula observed in the radio band. But the possible origin of this blob can be manifold, because we don't have clear and strong constraint about it. For example, it might be just due to some particular knots of titan-44, which is decaying and which is leading to some more intense radiation there. So why we are not seeing why we do not have any clear detection of this compact object, where it is likely because of the absorption of the cold ejecta, which I mentioned before, which is actually acting as a wall for the radiation stemming from the Pulsar nebula, or for the neutron star. Sorry. And since we have no detection, the only estimate that we can make about this object are the upper limits on its luminosity, which have been proposed based on either simulation point of view, like from Orlando and collaborators in 2015, but also from observational in various wavelengths, as made by Esposito and Alp in 2018. So what we have done is then to try to tackle this long-standing issue by analyzing some X-ray data in which we expect that the effect due to the absorption of the cold ejecta is more negligible. For example, we looked at the Chandra data, which are of 87A, which is here shown on the left, and to the NuSTAR data of the same target. These images give you an idea of how different the same object is seen from the two telescopes. Here in the 0.5 to 8 keV band, supernova 1987A can be clearly resolved. We can see the inner area where we expect that the neutron star should be, while for NuSTAR, because of its bad point spread function, we cannot resolve the inner area. So basically, this supernova 1987A is basically a point source for NuSTAR. If we look at the spectra collected by this region I showed, you can see it's well known in literature that we can fit this spectra with two thermal components, the one I was mentioning before, which shows undersolar abundances. So this means that we are not looking at ejecta, but at interstellar or circumstellar medium shocked. And the thermal flux is observed to be increased with time. However, there are no hints for an additional spectral component which might be associated with the compact object. If we take the same base fit model for the Chandra data and plot it over the Chandra plus NuSTAR data, which are here shown in green, we clearly see that some residuals at higher energy show up. And well, the first thing that we thought was, okay, maybe this is just another thermal component at higher energies that Chandra cannot see because it's not sensitive enough in that energy band. We tried to add another thermal component, but we found that no physically sound thermal component could be claimed to explain the observed residuals. Then the only alternative left is the non-thermal radiation, possibly the synchrotron radiation, which is emitted by 1987A, and could be emitted, for example, by the heavily absorbed Pulsar with Nebula. The problem is then how to take into account absorption, because since the plasma in supernova remnants is optically thin, we do not have any way to, we do not have like emission absorption lines or something like that. So what we have done is to take advantage of a state-of-the-art MHD simulation of supernova 1987A, which provides the ejecta distribution around the place of the explosion. We extract values of temperature, density, and abundance for each cell of this MHD domain, and we implement these theoretical information into the spectral model. We have then the following, the comprehensive model is then made by two thermal components, each folded with the telescope Chandra and NuSTAR, here in black and red, and also an absorbed power law, which is again folded with the Chandra data and the NuSTAR ones. What is critical here is that, as you can see, the absorbed power law in the range of sensitivity of Chandra is completely overwhelmed by the emission of the thermal components, which already explains why we cannot detect any, why we do not detect any emission in the Chandra data. By doing so, we are also able to estimate absorbing power, also taking into account the time evolution, because with time, the ejecta of 87A are expanding, their density is decreasing, and then also the absorbing power, which is due to a photoelectric effect, is decreasing. If we add this, it doesn't go, okay. If we add this absorbed power law to the Chandra, to the thermal components, and we plot and we fit it on the Chandra plus Pulsar spectra, we see the residuals that we were seeing before completely disappear in every epoch considered. The best fit photon index is of the order of 2, and it is constant with time, which clearly is a signature of synchrotron radiation as responsible for the residuals that we actually were seeing before. However, we have some statistical issues with our spectra, since at higher energies above 10 keV, the signal is not very high. And then to try to address this issue and to lower our uncertainties over these residuals, we made the so-called simultaneous multi-epoch fit. Basically, we put all the data together. We fit all the thermal components free to vary with time, so completely uncorrelated. We fit the power law component, and we leave it free to vary with time, but force it to be the same over the years. In such a way, we want to relate the residuals, the higher energy part of the spectrum from 2014 to 2012 to 2014. And the jet absorption component, which changes here, is coupled to the power law for each of the year considered. Thanks to this approach, we improved our uncertainty on the absorbed power law, on the power law component parameters. In particular, we found a photon index of 2.5, more or less 0.4, and a luminosity in the 10 to 20 keV band of roughly 3.2 times 10 to the 44 erg per second. Another scenario, however, which could be claimed to also explain the observed synchrotron radiation is the so-called diffusive shock acceleration, which is basically the theory which explains why we observe synchrotron radiation in the outer shells of supernova remnants in general. The main idea is that the particles shock cross the shock front back and forth, and every time they cross this shock, they gain a certain amount of energy. And according to DSA, the power law distribution of the accelerated electrons leads to a power law also in the spectra, in the photon spectra of the plasma, which with a photon index which is of the order of 2.5, so basically compatible with what we found. Here, I just recall a few quantities which will be relevant, such the acceleration timescale, which give us the timescale in which the electrons reach their maximum energy, the synchrotron emission peak, which is defined by these rules, by this equation here, and finally also the synchrotron timescale, which basically tells us in how much time the electrons reach some kind of equilibrium because of the energy that they're losing through the through the radiation of the synchrotron emission. All these parameters depends basically, or these quantities depends basically on the magnetic field of the velocity of the shock and of the eta, which is the acceleration efficiency, but also known as the bomb factor. So if we want to test the DSA scenario over the data, the only difference under a spectroscopic point of view is that here we have a power law which is not absorbed by cold ejecta, since, as I mentioned, the DSA is occurring in the outer shells of 87A, where there are no ejecta, of course. If we look at the difference values of the chi-square in the two scenarios, we see that we have just a slight improvement for the PWM scenario. But however, we cannot say that, of course, the radiation that we see is due to the PWM, because only a 1% improvement is achieved. Then we also measure the break energy of the electrons by fitting the data, and we found that according to values of magnetic field from 600 to 100 microgauss, we expect electrons of the energy of 14 to the 33 TeV. So if we make now some physical consideration on the DSA, first of all, we can look at the radio flux, which is known to be that of 87A, which is known to be due to the DSA. And we observe in between 2012 and 2014 an increase of 50%. Such increase in the history data is excluded at 90% confidence level. Also, if we take an average, a very typical magnetic field of supernova remnants of 100 microgauss, then the acceleration time scale will be of the order of 300 years, which is, of course, one order of magnitude higher than the actual age of 87A. And on the other hand, we need a very high magnetic field of 600 microgauss to account for the acceleration of electrons in a time scale which is compatible with the age of 87A. So all these implications make unconvinced the DSA scenario, even though it is still somehow possible. On the other hand, if we made some similar consideration also for the PWN, we see that by comparing the position of by comparing the Pulsar wind nebula with the known population of Pulsar wind nebulae, we see that we have a very good agreement between our the PWN of 1987A and the known population. Here, for example, I show this plot in which each brown lines marks the position of 87A, assuming a certain acceleration efficiency eta x. We made this assumption because this value has been observed in various Pulsar wind nebula to cover a very wide range of the order of 10 to the 4 order of magnitude. But to be as general as possible, we just released any possible assumption, and we see that for every of these values, we have a perfect agreement with the population. By also releasing the assumption of the density of the material which is surrounding the Pulsar wind nebula, as we have done here, we have a very good agreement between the known population and the Pulsar wind nebula that we and the characteristic of the Pulsar wind nebula that we found from our fields. So in the last minutes, I want just to give you some highlights about the Followup project, which we are basically finishing to work on. Since we have still this kind of degeneracy between the DSA scenario and the Pulsar wind nebula scenario, we made a step beyond the classical spectral fit, and we basically compared the MHD simulations. So we synthesized the spectra from the MHD simulation and compared them with the actual ones by extracting the temperature, the ionization age, and the electron density of the model and comparing it with the observed spectra. We assume abundances from the latest analysis of 87A, so from Sun and collaborators in 2021. We include the Doppler and thermal broadening effects when synthesizing the spectra. And the big pro, pro of this approach is that we have a physical interpretation of all the available X-ray data, because we are not using a phenomenological component, which is usually what we do with the standard analysis, but we use a model which is well constrained both from the progenitor informations and also from the supernova informations. We also enlarge the data sample. We consider data also collected by XM Newton, and we consider also the recently released 2020 data. So just to quickly show you what the comparison between the MHD model and the spectra doesn't go, okay, and the spectra look like. Here I show you, for example, the MHD model simply overlapped to the XM Newton RGS data, and which covers a energy band between 0.3 to 2.5 keV. As you can see here, the continuum and line emission are well reproduced. And what is important to highlight here is that we do not have any fit on the data. This is just the model taken as it is and plotted to compare it with the observed spectra. It is striking that we are able to fit not only the continuum, but also the line emission, which also provides some good constraint about the goodness itself of the model used to understand the data. And this is true not only for 2012, but also for 2014, as you can see here, and for 2020. The only thing about 2020 is that the MHD model seems to slightly overestimate the actual data. As you can see here, the ideal residual line is slightly above the data, especially at lower energies. Overall, we can say that the continuum line emission are well reproduced. Now, if we apply the same approach also for the Nustal, XMM, and Chandra data, we see that for the lower energy band until energy of roughly 7-8 kV, we have a good description of the data. But again, it seems that something is missing at higher energies. I want to stress that this is completely independent from what we have found with external analysis, because the model was not tuned or our analysis was tuned on the model. This is just recovering the same results by completely different perspective. And what happens if we now take the absorber power law from the standard analysis and put it and add it to this model? Well, this is what we get. Basically, we have a much better description of the residuals, especially above 10 kV. And this pattern is recovered systematically for all the years. So this is 2014, in which again you see the receivers at higher energies, and the spectra is very well fitted, while with the absorber power law component, which has this shape, we are able to improve our description of the spectra here. And for 2020, again, as you can see here, the model for over energies, which are not very interesting for our project, are a bit overestimated. But at a higher energy, we still see something missing here. And by including again the power law for the 2020, we obtained this good agreement. So overall, the MHD model seems to confirm that an additional absorbed power law must be included to take into account to properly explain the observed residuals. And finally, if I have just one more minute, can I?
Sure. Let's see.
Yeah. Don't worry. Just a slide. So, and also what we have done is to look at the flux between 2012 and 2020 of this of the 10 to 24, 10 to 20 kV band. And we see that while in every wavelength and in every different energy band, we clearly see some variation of the flux. For example, in this plot by Alpha and collaborators, we can see that in every wavelength and every band, we see very dramatic changes over the years. In this part of the spectrum, we are basically facing an almost constant flux. And we, thanks to the MHD model, we also found that the slight increase that you see of the order of 10% is due both to the increasing thermal contribution, but also to the decreasing absorbing power of the ejecta, which in 2020 are much less dense than in 2012, leading to higher observed flux. This means that the intrinsic flux of the PWN is constant, which is also something we expect for such a young Pulsar with Nebula. And then this other consideration also exclude the SA scenario as a possible mechanism empowering the observed flux in the new star data. I will just leave you with a summary, and thank you. Sorry for being a bit long.
Okay, let's close. Thanks a lot, Emanuele, for the nice talk. Any question from the audience? So while they warm up, I actually have one. So like when you talk about MHD simulate, like like the modeling and the fact that you get and you mentioned like progenitor, like mass, and that you said that you don't fine tune, right? So what do you use? Like in the sense that I know, like the group in by like Thomas, right? He was like able to reproduce the data also from like without any like fine tuning. But in your case, what do you do? Like you take some mass or like radius of the progenitor determined from other observations, and
so I have I don't know, I have some backup slide on that which maybe can be useful. So what I was not involved in the developing of the model itself. I was basically like taking the output of the model and implementing it and coupling it to the data. But what has been done is that basically you look at you take as a constraint some physical parameters which are well known from the progenitor star, from the supernova, and from the remnant that has been observed to evolve. And based on that, you try to, like, for example, recover the mass of the time 41 that has been observed, for example. But you do not fine tune the spectral characteristic of the data.
Okay.
So
okay.
You more or less describe the wall emission of AD7A, but of course the spectra are very sensitive to the condition of the plasma. So for example, here you can see that the morphology of AD7A is somehow reproduced, and of course this is based by the observations, but this is not true for the spectrum, which were just like an output, an indirect effect of the MHD itself. The spectra, on the other hand, suggests that the way the model was like tuned to the observation to fit other quantities is reasonable, because it matches also like the spectra, which is way more sensitive to the local condition of the plasma.
Okay, which is also like very nice. Also, that is one of the nice that Thomas and the Garshin group already did for ALMA data, right? In which there was basically no fine-tune required on the model. To explain it. And actually, Thomas has his hand raised. So Thomas, I think that you can go ahead.
Thank you. Yeah, I think I've unmuted myself. Thank you for this interesting talk. Of course, I know about this proposition of the Pulsar wind nebula, and at the moment we have, I think, two possibilities. On the one hand, we have discussed the blob and its emission possibly being linked to a thermally cooling neutron star, while you read from the X-ray data, X-ray access, that it might be a Pulsar wind nebula. So, I mean, I have a comment and a question. Very quickly, the comment explaining this extra emission, I mean, which is really at the resolution limit of the ALMA observation. But if this blob emission comes from titanium-44, it would require an enormously strange concentration of titanium. So titanium would have to be quite there would have to be quite an amount of titanium in a small volume, and also there would have to be a huge amount, nearly a solar mass of material to trap the gamma emission from the titanium and to convert it into this long wavelength radiation. This is not really plausible. So I would say this would be very, very strange tuning.
Okay.
But I have a question for you now with respect to the X-ray resolution. Do you have any idea from the X-ray data where you would expect this emission to be located, or where the neutron star should have to be if it were a pulsar?
Yeah, let me take the. So basically, now if you look at this image from Chandra,
yeah,
it must be somewhere within the black circle here. Now the problem is that, as I showed you, with Chandra, like in the range where Chandra can see, we do not have any radiation because of the absorption. At least this is our idea. While with new star, which could be sensitive to it, you can see here that it's just a point-like source, so we have no special resolution, we have no info about the morphology of 87A. If we had something which has the spatial resolution of Chandra and the sensitivity of new star in this band, then we will probably see the Pulsar wind nebula in the central part of the image. But this is basically just a lack of the right instrument to actually see, to directly see the image, which of course we can directly see the neutron star, which is something that of course we cannot do right now.
Mm-hmm. And the second part of the question, may I ask it?
Yeah,
of course. Go ahead.
Thomas. Yeah. What would be the total luminosity compared to the grad pulsar if you take this excess X-ray emission as a pulsar?
We have another backup slide which maybe can answer that. So in our new follow-up paper, we are trying to also to put some constraint about the PP dot diagram, like where the neutron star should be. We compared it with the findings by Page and collaborators, and basically we are in agreement with them because Page found something which is an upper limit on it, because I remember that they say that they assume that all the radiation that is observed in ALMA comes from the neutron star, while of course you can always there must always be some part of the radiation of the neutron star which does not go directly into the blob, right? You of course are missing at least a certain amount of it. So this band here is basically the upper limit, the lower limit on the luminosity, but it might be higher. And actually what we found with the X-ray data is that we have a slightly higher, not very different, slightly higher range for the possible luminosity of the Pulsar nebula. So I will say that our results are indeed compatible with the ALMA data and also with the suggestion from Page and collaborators, which I guess was the one you were referring to.
Yeah.
Okay, so I don't see other questions. So if they can say this is the case, we thank Emanuele again, and we go we stop the registration for this talk and we go to the